speaker is here? Yes, yes. No, no, no. No, no, he's Mr. Schulze. He's not the first speaker.
Oh, sorry.
I think we are still waiting for the first speaker. So please, yeah, relax and take your time and yeah, get comfortable.
Sorry, I misunderstand. He's not the first speaker. Huh? He's the speaker?
No, he's not speaker. This is Dr. Schulze.
Oh, I
He's
see.
the head of working group B.
Oh, so you know him very well.
But we have basically two speakers.
Hmm?
Yeah, maybe there has been a change also in the computers and on the programs displayed in the app. So maybe there is a misunderstanding on the rooms. I don't know. We are just checking at that time.
Really?
On my application, it shows this session T32 starting at so we are in the correct room.
First speaker. He.
Okay.
Just a moment. I talked to him. Here is
Yeah.
Okay. Okay. Yes. Okay. Room is okay. Room.
Everything is okay.
Okay. Yes. So, good afternoon. Please welcome to our session. We will start probably 3 minutes. Okay. Okay. So, I'm Yoshi Kaneda from Japan. And Coach.
Yeah, good afternoon, everybody. My name is Xavier Blanchard, working at the CTBTO OSI division. So it's our pleasure to have Professor Kaneda also chairing this session. The session this afternoon is on laboratories and mobile and field systems. Laboratories for the treaty are very important for several reasons. They allow confirmation of sample measured from stations. They also provide much more precise measurements. And especially if we can bring to the site mobile systems, it's also very interesting and powerful capabilities, also in terms of applications for on-site inspections. So this afternoon we will start with 2 oral presentations on such recent developments. Then we have 15 minutes discussions where you are, hopefully you can engage in some key questions about what should be next developments, what should be the best scientific input to the development of such capabilities. And from 2:15 to 3, we will have the poster previews. We've been informed by conference services that maybe not all the poster preview slides have been downloaded, so it may be that there are still authors that would like to present their work, maybe not with the poster preview slide, but still we will remind you just before 2:15 to 3 that you should get prepared and come up to the to this place to present your work.
Yes.
I'll hand over the floor now to Professor Kaneda for the first oral.
So I would like to start this session. I would like to introduce the first speaker, Dr. Pakomov-san. The title is Mobile Sampling and Measuring Complex SARS. Okay, Dr. Pakomov-san,
Thank
please.
you. Good afternoon. My presentation is Mobile Sampling and Measuring Complex SLARS. On-site inspection is a key element of the verification of state parties' compliance with the Comprehensive Nuclear Test Ban Treaty. One of the evidence of an underground nuclear explosion is detection of argon-37 in near surface air above its background concentration. The background in subsoil to underground explosion, the concentration of argon-37 can exceed the ground from 4 to 7% orders. Argon-37 decays through electron capture, emitting low-energy X-rays and Auger electrons with energy of 2.6 kiloelectron volts. The methods of its measurements, millibecquerels per cubic meter, is technology feasible. Currently, only Mars system created by INPC China is capable to measure the subsoil argon-37 at the level of 26 millibecquerels per cubic meter. Its measuring part is based on the proportional counter of 2.5 liters capacity of argon. The further increase of the sample volume and therefore the sensitivity is hard to achieve without major complication of the system. The Chlopin Radium Institute has developed the conception and pre-project of mobile sampling and measuring complex SLARS, abbreviation of subsoil liquefied argon scintillations. It is intended to measure argon-37 in subsoil air sample of 2 cubic meters at a detection level better than 20 millibecquerels per cubic meter, having used the condensed argon sample itself as a liquid scintillator. The scintillation of liquid argon consists of fast and slow components. The slow components is subject of quenching owing to capture of electrons by oxygen and other gases. Without quenching, the light emission yield reach 40 photons per kiloelectron volts or 100 photons per decay of argon-37. For comparison, liquid xenon light yield reach about 70 photons per kiloelectron volts. The wavelength of liquid argon scintillation is in the far vacuum ultraviolet region, and its direct detection requires fragile and costly PMT with magnesium fluoride window. However, the xenon dissolved in small concentration in liquid argon provides a shift of the slow component wavelength from original argon wavelength to xenon wavelength in a region where usual quartz windows are transparent. As an acceptable alternative for expensive special, oh sorry, I missed the list of PMT designed by Hamamatsu Photonics, especially for registration of short wavelength photon. Okay. That PMT presented on the picture. As an acceptable alternative for expensive special PMT, the Hamamatsu R331 can be used as its sensitive band overlaps xenon wavelengths. Also, more specialized Hamamatsu R375 can be used, which efficiency reach 20% at the 175 nanometers wavelength. Their spectral response and other main characteristics are shown in next figure. Really, okay. Really, we see that the region of sensitivity overlaps the short waves. Okay. Except the xenon doping as a wavelength shifter, it is also possible to cover the PMT window with a layer of wavelength shifter, like tetraphenyl butadiene, transforming the primary photons into the photons with the wavelengths on 420 nanometers, the area of maximum spectral sensitivity of the usual PMT, such as R331. Calculated probability of registration of number of photons depending on PMT quantum efficiency Да. 1, 2, 10, and 20% of quantum efficiency. These calculations are made in the assumption that the 100 photon emission corresponding to decay of argon-37 in liquid argon without quenching. Apparently, at efficiency more than 10% are possible, forming the isolated peak corresponding to the energy of 2.6 kiloelectron volts. The functional scheme of a measuring system of complex layers is presented on figure. In a cylinder, there are from 10 to 20 liters of purified argon extracted from subsoil air, sample doping with 100 ppm of xenon. This sample is transferred into the measuring camera where it is liquefied. In the measuring camera, a small excessive pressure remains for prevention of impurities. The required cryogenic temperature is provided by a compact Stirling cooler. Compressor, cooling head. The photons are focused on an input window of PMT R375 or R331, optionally. In the last case, the TPB layer for a wavelength shifting is used. The PMT pulses come to the fast preamplifier and to the ADC and comes to PC for final processing. The principle of work of sampling part of the slurs is based on the process of short cycle pressure swing adsorption. The sampling system contains two symmetric paths, upper and lower. Working alternately. The sample of subsoil air is transferred into one of the soft gas holder in the up, in this case. And by means of the compressor pumps into the one of the part of the dividing columns. And the other part of this, at this moment, is regenerating. The column is, the column 3 is filling by special zeolite. The column 4 is filling by carbon molecular sieve. After filling under required pressure, column 3 is connected with the column 4. The working cycle of column 4 has duration about 10 seconds. After its completion, the column 4 is connected with buffer reservoir 5. By means of the compressor, obtained argon fraction is pumped into the accumulation cylinder 7. After the completion of the cycle, the column 3 and 4 are regenerated by means of the pump 15. Products of regeneration are accumulated in the opposite soft gas holder for repeated processing. About 100 liters of air are processed on each cycle, and the duration of a working cycle is about 1 minute. 20 working cycles are provide all initial amount of subsoil air sample processing. As the efficiency of extraction does not raise high, the processing is repeated 2, 3 or more times, providing the obtain of total argon output about 60%. From the storage cylinder 7, the raw argon is pumped into the chemical adsorbers of nitrogen and oxygen. Further purification of argon to the required level of impurity is processed by means of fine purification device. Obtained argon sample is pumped into the final storage cylinder. So, the estimated main technical characteristics of mobile sampling and measuring complex slurs are amount of air processing 2,000 liters, processing time up to 5 hours, working pressure up to 6 bar, working pressure, amount of extracted argon sample up to 20 liters, content of impurity in an argon sample less than 1 ppm, capacity of the measuring camera 30 cubic centimeters, efficiency of registration 95%, background 0.1 counts per second, measuring time up to 12 hours. MDC of argon 37 about 20 millibecquerels per cubic meter. Thank you for your attention.
Thank you, Dr. Pakomov. Any questions, comments? Yes, please. Xavier-san, please.
Thank you very much for a very interesting presentation. I think there are actually several
Thank you very much.
several efforts right now ongoing about sampling and processing of argon to be measured in the field. There was actually also another topic, 3.1, earlier this week, where posters presented also such efforts. We can discuss later on with Dr. Pakomov some specific details. What is interesting is to understand maybe how you could improve further the capabilities of the system and lower the MDCs. I think some other systems mention that they can go even below the 20 millibecquerel per cubic meter. So now we can move to maybe the second oral, unless you have one or more question on this specific topic. But so the second presentation will be on xenon sampling, and this will be for measurement of atmospheric air concentrations of xenon versus, so you understood this first presentation was on subsoil sampling and measurement.
Yes.
So Dr. Dubasov, also from the Klopin Radium Institute, will present this second development.
Good afternoon, everybody. My name is Yuri Dubasov. I am from Klopin Radium Institute. I tell about our development mobile laboratory for noble gas analysis in atmospheric air. This development was in frame of STC project at Canadian financial support in 2008. This our installation has productivity of 20 cubic meter per hour and MDC for xenon 133 0.45 millibecquerel per cubic meter. Main process for sampling and processing of xenon and krypton from atmospheric air is cryogenic sorption on activated charcoal. The turbo expander used for cooling atmospheric air, where the minimum temperature minus 100 centigrade was achieved after 6 hours. Temperature 80 centigrade achievement after 1.5 hours. Xenon extraction efficiency is near 50%. Spectrometer of beta gamma coincidence consisting from HP germanium detector and beta camera in form Marinelli bottle was used initially. Then scintillation sodium iodine spectrometer beta gamma coincidence is used now, and sodium iodine scintillation and silica pin detector spectrometer now being developed. This figure you can see temp of cooling air by turbo expander. Our system has name Ringa F. It is a Russian installation noble gas analyzer field. You can see this slide main units. No. This?
What?
No, laser. In these units together sampling and processing unit. This portable chromatograph, also Klopin Radium Institute development. On this slide you can see our beta gamma spectrometer, beta gamma coincidence spectrometer. It is first spectrometer consists from HP germanium detector and Marinelli bottle. This now used scintillation beta gamma coincidence spectrometer. Main characteristic our installation: sampling pressure 7 bar, sampling flow rate 20 cubic meter per hour, maximum productivity 140 cubic meter per cycle, sampling time from 3 to 7 hours, concentration or separation time 3 hours, radon depletion factor 10 order in 5, deployment time from 2 to 3 hours, set up time for start up nearly 20 minutes, dismantling for transportation 5 hours, detector C system I talk about, MDC MDC for xenon 1 tori-free 0.5 when we conducted monitoring. We started monitoring of nuclear power area near nuclear power plant. We started in 2008. This slide you can see vent duct of Leningrad nuclear power bore. Next, next xenon 1 tori-free 0.4 millibecquerel per cubic meter, 1 tori-5 xenon 0.3. Ratio these isotopes 0.7. During monitoring, concentration indicated xenon change in interval from 0.5 to 8 millibecquerel per cubic meter for xenon 1 tori-3 and xenon 1 tori-5 from 4 millibecquerel per cubic meter to 53. Kalinin and Kola power nuclear power plant. This background and concentration was was less than nuclear NPP Leningradskaya. This Kalinin NPP, this picture is Kola NPP. Xenon radionuclides background in air of with NPP area distance from 2 through 18 kilometers, variation in interval 0.5, 1.8 millibecquerel, of course, sorry, millibecquerel per cubic meter. So, Ringa F system productivity is 20 cubic meters per hour, allow for sampling air for 3 hours, and xenon MDC will be 0.3 millibecquerel per cubic meter. This installation has been used to xenon monitoring around of Leningrad, Kalinin, and Kola NPP, as well as in the Vologda region, far away from NPPs, nuclear power plants. Almost all component and installation units, despite the great distance traveled, about 1,200 kilometers, were intact and functioning. Ringa F system was transported by 2 off-road cars. Minivan was Russian model, or can place in minivan Volkswagen Crafter 3045. So, Ringa F system currently operates and has been improving. Thank you very much.
Thank you, Dr. Dubasov-san. Any questions, comments?
Thank you.
You have, we have a question in the room?
No,
or?
no.
No, I have one to Dr. Dubasov. You mentioned that so the total weight is 300 kilos. What is the highest weight of a specific module? Thinking in terms of a potential deployment in the field?
50 kilograms, main module, electric generator near 40 kilograms, total 300 kilograms.
And are there limitations in terms of consumables, or because I think in the summary slide you mentioned 3 hours operations, and in the previous slide you mentioned from 3 to 7 hours. So what are the key elements to calculate the operation time?
It is needed it is determined by noble gas concentration in atmosphere.
Yeah, so
If very low atmosphere, then we sampling 7 hours. If more, then 3 hours.
And the MDC you mentioned of 0.35 millibecquerel per cubic meter, is this with the germanium detector that you mentioned, or with the Marinelli bottle, or with the beta gamma coincidence?
Equal.
Is the same?
Yes.
Okay.
Other questions from the room?
Thank you.
So I think we can thank the two speakers.
Thank you very much. review?
So we can have actually now a more broader discussion. We have seen examples of development of key transportable systems that would be very useful for the application in on-site inspections. I would like to hear from the room if some other participants have different experience that they would like to share or specific questions for such systems. What main areas, according to you, should be improved, or what are the? Actually, argon is a very nice example because it's very difficult, as Dr. Pakomov said. It's one of the most difficult elements to separate, concentrate. So do you expect that new technologies on adsorbers, we have discussed later on, earlier, sorry, this week, new adsorbers, do you expect also improvements in such techniques? What is actually right now keeping the MDCs still a bit high? I know at PNNL you have also very recent developments of transportable equipment. This was presented in another topic, 3.1, but maybe it would be also interesting to compare the size, the number of modules, how modular your system would be also to be deployed in an on-site inspection. Is it actually something that can be deployed in the field, or would have to be installed in a kind of laboratory setup? Okay, maybe you want to reflect on some of these issues.
No questions?
We will have also later on, I think this afternoon, Dr. Boyer will give a talk on argon measurements in the atmosphere and its possible use for the IMS. Here we are talking in terms of laboratory capabilities and also specifically of the interest to have compact modularized systems that are transportable to the field. But argon will be discussed later on this afternoon, and there is also a very interesting talk that you could attend. I think it will be tomorrow early morning, where Dr. Puchert from Switzerland will present also measurements done from argon samples. Sorry for that.
No.
In the field, yeah, Ted, do you have some comments?
Yes.
So to answer your question, yes, it can be operated in a on-site inspection-like scenario. There's a booth from a company named Teledyne Brown that shows the configuration of that system, the Z9 International system. So that's just to answer your question. I have a question for Sergey. And this has to do with the energy resolution of your liquid argon, well, the technique you're using. And the question has to do with discrimination between argon 37 and argon 39. We have found that on a number of occasions there is an argon 39 background, which is a relatively low energy beta emitter, but does form a background for the Auger electron.
Okay.
Okay. I will try to first question. The resolution, the energy resolution of in argon spectrum was obtained by means calculations in Monte Carlo manner. Simple calculation. It's a statistic. When the quantity of photons enough, the resolution becomes itself. Okay? First question. Second question, it's my answer more simple. The China device not consider the argon 30, what you say, 39, or only 37, and I too. That's all.
Okay. Second.
So I'll just expand on that, the argon 39 issue. I did a poster, and we did some measurements out at the Nevada test site, the former Nevada test site, and measured high levels of argon 39. It was a poster that we presented. In retrospect, it seems obvious that that should have always been a signature that was available in for nuclear explosion. With that, now kind of with that knowledge, I think we need to start looking at that and incorporating that into the argon 37 MDC values that we achieve. It may not be so important that we get down to very low levels, number one. Number two, is argon 39 something that the on-site inspection committee or the on-site inspection regime, is that allowed? You know, what are the implications of it? If the physics, it's going to be there, unless you've got absolutely potassium-free soil, which is unlikely. So that I think that's kind of a development. And having our two presenters come from Russia, I would encourage you both to make some measurements at your test site and see if you confirm the results that we found earlier. So.
Thank you. Any questions? Comments?
So the session is also more broadly on laboratories. And we have also participants here from the laboratories that support the IMS, maybe other laboratories that are not part of these 16 laboratories. So you may express also your opinion of, let's say, for example, the quality which is necessary to be assessed for mobile systems versus laboratory systems. The PTS is putting a lot of efforts in proficiency test exercises also to have the systems participating in intercomparisons. So I guess in the near future we will be quite happy to have measurements from such mobile systems participating in similar intercomparisons. PTS is also gaining a lot of experience with new capabilities within these laboratories for noble gas measurements. So the first noble gas capabilities have been certified from CTBTO in the recent years, and this year there should be even more laboratories. And actually, so on several of these topics, either you would like to comment and now share your views with the room, and maybe if not, we can proceed with the poster previews, and then you will be invited later on this afternoon to go through the posters in the Festsaal. I would also like to remind you that you have till tomorrow 11 also to vote for your best oral or poster. So please do so, and don't forget to drop the card in the boxes that are available by conference services. Maybe one question here, Jim?
Yes, Xavier, I just wanted to comment on the argon system. We did, we had the mobile argon system poster briefed in a previous session, but if you want to see what we've done on the argon 37 system at PNNL, it's poster T3.1 P18. And I can be there, or others from PNNL can be around. So if you want to see what we've done, we've got 5 different modules that separate, purify, and measure argon in the field. And so then I also wanted to ask about the lab system. There's a lot of round-robin samples being passed around to the laboratories. How and what decisions are being made about the concentration and the ratios, and what's the strategy on how the samples are being chosen for the round robins?
Well, if you are talking in terms of argon, I don't think that there is now such, or are you
Sorry,
talking about xenon?
I jumped subjects. For the laboratories for the xenons that you do send around the round robins, just curious about how you're making the choices of what you're sending, what the ratios are, and what the activities are.
So maybe we have people here from the CTBTO IMS that would be able to comment on the selection. But basically, the strategy is to test both the capability of systems, laboratory systems, to identify the key relevant nuclide, so at some high activity level, so that you can actually extract the various interferences, and also test the sensitivities of the systems with samples of lower activities. But of course, these results are discussed especially between the laboratories supporting the CTBTO at working group B sessions. And there has been already some exercises to collect experience on such proficiency test exercises. And you are welcome to discuss these results. There will be, by the way, the next working group in August, so probably we will have new results there in August that we can discuss, and at that point maybe see if we should expand or concentrate on specific ranges of activities.
Okay.
So if we have no more comments from the room, I would invite the presenters of posters to...
Okay. So I'd like to move on the poster preview. So the first poster number 1 is, please, come to, please.
And so if the next presenters can...
Number
get
2
prepared.
and the number 4, please. Please.
Hello, my name is Eka. I'm from Indonesia. For this session, I will make a poster presentation for determination of fusion radionuclides, strontium-90, and plutonium-242 in water sample. Thank you.
Next speaker, please.
Hi, my name is Matt Goodwin from the UK. I work at AWE. This poster is not mine, but it was put together by my colleagues Richard Britton and Ashley Davis, some of you might know, and it's on the gamma-gamma coincidence system that we've got set up. I'm happy to talk about it with anyone interested, so come and have a look. We've also got a couple of posters related in the same room, so feel free to come and have a chat. Thank you.
Thank you. Thank you. Poster number 4, please.
Good afternoon, everyone. So, certified labs are playing a significant role in the IMS network because they are in charge of in-depth analysis of suspicious samples that may be collected on the field. So in our lab, we spent the last couple of years to extend our certified analysis from particulate samples to xenon samples. So it turns out that these analyses are much more challenging than the particulates because we are trying to measure a gas and we have to purify it and to take out the xenon and a lot of stuff. And also we are very much hampered by the short half-lives. So please feel free to come and see our poster and we'll show you all the gadgets that we set up in order to perform this analysis. Thank you.
Thank you very much. More? No? Okay. Okay, sorry. Poster session will start from 4 p.m. Okay? Please come to poster session.
So I think we can close the session now. Thank you very much for your attendance, and also we have Jim Hayes, who offered to be there also to discuss his poster that was actually presented also in session 3.1, so that's poster 18, if I noted correctly.
Okay.
We're now, so we close the session. Thank you very much.
Thank you very much for your coming and attendance. Thank you very much.
Thank you.
Yes, so they... So just, I think you may start and introduce yourself, and then we will introduce, each of us will say.
Yeah, we'll give it maybe one more minute because people are still coming in.
And then we will meet again tomorrow.
Yes, in the morning, right?
Yes, exactly.
Okay. Good afternoon, ladies and gentlemen. Welcome to session 1.3, Atmospheric and Subsurface Radionuclide Dispersion and Depletion. My name is Glenn Chadine. I'm the Chief Scientist at the Air Force Technical Applications Center in the United States, in Florida. I'd like to introduce my co-chairs, Jolanta and Boshu. If you could take a minute.
Okay. My name is Jolanta Kuśmierczyk-Michulec. I'm an Atmospheric Sciences Officer at IDC.
My name is Bo Xue Liu. From the IDC, I'm a radionuclide officer. Thank you.
So our first...
They're going to have to switch them,
Okay, okay, then you start.
Yeah, there's a technical difficulty with the first speaker's paper, or slides, so they want to go ahead and they've asked us to go ahead and have Dr. Bowyer. Ted, can you give the talk that you want to give on argon-37 measurements? Thank you very much, Ted, for being flexible.
No problem, Glenn. Good afternoon, everybody. My name is Ted Boyer. I am going to talk about argon-37 measurements and how they might be used in a coincidence with the radio-xenon measurements. And in this case, not for on-site inspections, but for the international monitoring system. Well, this is probably a slide that I don't need, but it took me a long time to make those little red balls and blue balls and put them together. And I was so impressed with my ability to use PowerPoint, I just thought I'd show that one. But argon-37 is produced by activation. It's not a fission product. It's produced when neutrons interact with the soil. I don't know how to use the laser on this thing, but one of the buttons. Yeah. So the neutron interacts, the higher the energy neutron, the better. Interacts with calcium-40 that may be in the soil and goes through what's called an N-alpha reaction, creating argon-37. So as far as motivation goes about why I'm looking at this and why I think that the scientific community should be interested in this is because we've had a number of cases in operation of the IMS where the measurements done at the stations had some issues. It wasn't issues with the operation of the station. They worked fine. They made the measurement appropriately. The problem was very high backgrounds from man-made sources. So we couldn't understand always what that measurement meant. If there was a nuclear test, it could have theoretically not been seen because of the xenon-133 background. It's been very frequent. And there's been other presentations at this conference and other conferences. For example, Judah Fries on, I think, Monday gave a presentation on that, and there's a number of posters discussing this issue. The situation is getting worse. It is not getting better. And that's because the number of radioactive xenon-133 atoms in the atmosphere depends on the number of medical procedures that occur per year. The population's going up, the use of the technique is going up, and therefore the background is getting worse. So I was motivated, and other people have been motivated to try to fix this problem, trying to find ways to around the increasing backgrounds. Here's just a summary of this. I think Judah probably covered in his presentation. What I want to draw your eyes to are the colored, especially the red colors. And what we've plotted here is the number of days in a year where if you were at that spot making a measurement, you would detect radioactive xenon from a man-made peaceful source. For example, in the most red color, between 240 and 365 days a year, you would see detections above the detection limit. And at some places, it's incredibly high levels. So that's what we're dealing with. So we're trying to find ways to mitigate the effect of the Moly-99 production. Okay, so that's as a backdrop, sort of the motivation about why we're looking for other solutions. I will also note that argon-37 is a relevant radionuclide for on-site inspections. Already been agreed, been discussed for years. There's a number of pieces of equipment out there. Roland Puchert and Robin Riedman have done a lot of work in this area, and there's probably a poster or two, maybe, or in a presentation maybe Roland's going to give, discussing argon-37, but only for on-site inspections. It's not been discussed seriously for IMS. Also at SnT 2015, there was a really good presentation made by Li Wei from China about measurements of argon-37 in the subsoil, again, really for on-site inspections. But if we're looking for argon-37 for on-site inspections, it makes at least some sense from the perspective of harmony to look at argon-37 for the IMS. And now I've tried to put some harder numbers to the word harmony and explain why I think it's worth taking a closer look at. Okay, so I have given a form of this talk in the past, and the first question I got was, are you replacing xenon-133? I want to make sure people understand that I'm suggesting augmenting, I underlined it, I was going to make it bold also, but augmenting the current signatures, because I still believe xenon-133 is among the best, if still not the best signature there is for radionuclides. So I'm not suggesting replacing it. If you recall that map with a lot of colors on it, there are still a lot of colors that are white, which means it probably wouldn't be detected at that location many times. So I am suggesting augmenting the IMS with another radionuclide, another noble gas signature, in this case argon-37. And I'm going to try to convince you that it is, in some cases, a better signature than xenon-133. In some cases, it's not. So ideally, if we had our druthers, this would be based on, the argon-37 for the IMS would be based on modification of existing technology. That would be the cheapest, fastest, probably most efficient way to do that. And as I mentioned, the Chinese system and the US has a system now to make argon-37 measurements. I claim that those can be modified for IMS applications. So in a nutshell, argon-37 is a noble gas, which means it's very likely to be emitted from the subsurface in a nuclear detonation, just like xenon-133. It's got a perfect half-life, really, for CTBT. 35 days. 35 days is long enough that it has time to come up from the subsurface, but not long enough that it would build up, probably, in the atmosphere. We don't know everything we'd like to know about backgrounds, but we do know some, and I'll talk a little bit about that, and I think Roland may cover that in his presentation. Also, I know that there's a presentation being given tomorrow by Anna Heiss, and I don't know, tomorrow though, right? Okay, so it would be great if she was in the same session as I, because then she could say everything right that I'm saying wrong. But the yield for those radionuclide people that are in the crowd is between 10 to the 13th and 10 to the 14th becquerel per kiloton of explosive power. So what is the advantages? I went through some of it already. It's got, I consider, the perfect half-life, 35 days. I claim that the argon-37 may be low, in quotes, on some places on Earth. However, it is likely, since the sources of argon-37 is not going to be medical isotope production, because medical isotope production involves fission Argon-37 is an activation product. Anyway, the background will be likely different than for xenon-133, at least in some cases. And therefore, if you detect the two isotopes in some kind of fusion, looking at both at the same time, that should be able to give you additional information. In other words, where the xenon-133 background is high, you don't necessarily expect the where the xenon background is high, you don't necessarily expect the argon background to be high, even if there are sources of argon. Okay, so in other words, coincidences are going to be useful here. I mentioned it's pretty high, the background level, that is the becquerels, that's the number of atoms essentially produced per kiloton of explosive yield is pretty high. That depends on soil conditions. And there's been a number of calculations that have been done, and there's a number of measurements that have been done following nuclear detonations. And frankly, the Argon-37 numbers are exceedingly high in those measurements. So with regards to the production yield, how many atoms are produced? It's pretty easy to calculate for xenon-133. That's as simple as the fission cross-section. I'm sorry, the fission yield for xenon-133, the cumulative yields, which is the maximum that you can get based on the parents decaying into the xenon, is in the range of about 10 to the 16th becquerels, and that's after 3 days. The estimates that have been done via calculation and some measurements are between 10 to the 13th and 10 to the 14th becquerels per kiloton. Don't really want to quibble on whether it's 10 to the 13th or 10 to the 14th here, but I can refer you to a number of papers where that's done in some detail. It is, you can see, it is lower, but I'll explain to you in a second, I hope, why I don't think that's always going to be an issue, that it's a factor of almost 1,000 lower, because the background can be much lower. This depends also on the amount of calcium in the soil. These calculations assumed a few percent of calcium. I think 4% is what most people use as a global average for calcium. And in these calculations, a watt spectrum was assumed for the energy of the neutron. The Argon-37 production depends highly on the energy of the neutron. The detail, and there's detailed simulations in the University of Texas papers and others that I will refer you to. Okay. Source term. So this is, I mentioned the production mechanism. It is via a neutron interaction on calcium, yielding an alpha particle and an Argon-37. And Argon-39, as we talked about just about 10 minutes ago, is also produced in similar reactions, although that's a neutron-proton interaction on calcium-40. I have both of those plotted here. And as you can see, what's plotted here is the cross-section in Barnes versus neutron energy. As I mentioned, a watt spectrum was used to calculate those numbers for Argon-37, and it is highly dependent on the energy of that neutron. Justin McIntyre's poster is about the Argon-39 problem. It is also produced in high quantities in some cases. So what I showed here, and I'll show again in another form, is the amount of radioactive noble gases as a function of time from a nuclear detonation, assuming about 10 to the 14th becquerels per kiloton. Okay, so what we have, and the ones you should look at probably, I'll try to guide your eyes to it, are the blue and the orange. Orange is xenon-133 as a function of time. This is days. This is the number of becquerels created. And as you can see, the xenon is much higher, but that's not forever. At around 80 days or so on this plot, the amount of Argon-37 is actually higher. And so that's quite significant, especially if you combine that with the most likely amount of background that you're likely to see. So to put a little bit more numerics to this, I came up with a figure, what I call a figure of merit, which is something what you might call the detectability, comparing the size of the likely signature in the atmosphere to the expected background of that isotope. You could also do it by the square root of the background. There's just different permutations of that. They give approximately the same answer. Another figure of merit is the selectivity. And I've talked a little bit about the background sources of Argon-37. And another figure of merit, of course, is costs, about how much it would cost to use these different isotopes. So I'm going to concentrate on the detectability figure of merit. So what I've shown here, and I know this is a bit of an eye chart, there's a lot of plots here, but this is sort of in graphical form all of the noble gas isotopes that are likely to be produced from a nuclear test. And what I have here is the best case figure of merit and the worst case figure of merit, and that varies as a function of what you might think the background is, which we have an incomplete knowledge of. So what I show here is and what you want is a high figure of merit in my calculation. And what it shows is argon-37 actually has the highest figure of merit of any noble gas isotope in places where the background is low. So that's consistent with what I mentioned earlier, is that after some number of days, the argon actually has more activity available to be measured than the xenon because it's got a 5-day half-life, and argon-37 has a 35-day half-life. I'll say that my figure of merits are estimates, and that's primarily because there's an incomplete knowledge of the backgrounds of argon-37. All of what I'm saying is complete nonsense if the argon-37 background is indeed high across the Earth. We don't know that. We do know it in some places. I know there have been measurements by Byrne and others, but I claim in some places that the background is likely to be low. And that's why we should continue to look at it. So now in a graphical form as a function of time, this is the range. The dotted lines are the range of the figure of merit for xenon-133. But in this plot, before about 45 days, xenon's always better than argon-37. But after some 45 days, in some cases, argon's actually a better figure of merit. So how do you interpret this? At greater than 80 days, argon-37 is generally speaking a better half-life because of the half-life. And that's one of the reasons I think we need to continue to look at this isotope. This is even more relevant today than it was 5 years ago because we saw in the 2013 test that there was a delayed release of xenon of 55 days. So that's a relevant detection scenario, is a very, very far delay of the emission. When the xenon backgrounds are very large, like greater than 1 millibecquerel per cubic meter, and if you remember my map that had many colors, there's a lot of places where the background is higher than 1 millibecquerel per cubic meter. Argon-37 is probably better because of its half-life and because it's likely to have a background that's in the range of 1 millibecquerel per cubic meter or lower. And if xenon's very high, for example, near medical isotope production, argon-37 is almost always going to be the preferred signature because it is not likely produced in that process. So why hasn't this been done before? Why didn't we start with argon-37 20 years ago when we were negotiating it? Well, the bottom line is argon-37 is a difficult isotope to measure. Sergey, I don't know where Sergey is, but he mentioned that. It's got a very low energy, maybe it's 2.6 keV Auger electron. That's a challenge. It has to be measured in a certain way. Maybe that is through internal proportional counting, as Jim Hayes' poster, he mentions that on his poster, I believe. Or maybe in the way you have to liquefy argon. But it's a difficult thing to do. And the chemical separation to remove argon from air is more difficult than xenon. So that's main reason I believe it hasn't been done. There weren't a lot of examples of argon-37 measurements when we negotiated the treaty. We're in a different situation now. We have argon-37 technology for on-site inspection, which I believe can be adapted to the IMS case. We still, as I mentioned, have incomplete knowledge of the backgrounds, however. So I wouldn't tell anybody I'm ready to invest my money in argon-37 now, but I am ready to invest the government's money to do research. And that's what I think we need to do. And we need to do more in terms of measuring backgrounds across the world and doing modeling like we did for the case of medical isotope production, trying to better understand how big the backgrounds are, what produces the background, is it only nuclear reactors, et cetera. I'll just say one or two words because I think I'm running out of time about the fusion of argon and xenon. I think at the minimum, the use of argon-37 when you detect it in coincidence with xenon-133 will be a fantastic signature and could improve the situation even when the xenon backgrounds are high, or even when if either isotope is high. I also went into this that the xenon-133 is an exceedingly high background some places. So in some cases, in conclusion, argon-37 is better than xenon-133. I'm not saying it's always better or even competitive necessarily in many places in the world, but it is something that we ought to look at. We ought to collect more data, trying to do things like making measurements at IMS stations, which has been done on a case-by-case basis. We need to model reactors as a source of of argon-37. I think some of that's being done. We need to continue to work on source term models from nuclear explosions to understand both the fate and transport of argon from the subsurface and the amount that's produced, and look at the background. And finally, we need to adapt OSI systems so they're more sensitive, as would be needed in the case of the IMS. And that's all I have. Thank you.
We should probably move, I think there are a few questions, but we should probably move on to the next talk.
Our second presenter is Christian Maurer, and he will present the results of the second ATM challenge that was organized last year.
Oh, well, thank you. Let's start. I'm still missing my slides. Yeah, so I'm glad all technical difficulties have been solved, and we are now able to dive into the topic of the so-called second ATM challenge 2016. I mean, many of you in the last few days will have probably come across this topic. So it was a very comprehensive work, so I will only be able to supply you with certain cornerstones of this exercise. And of course, I have to mention that there was a contribution from a lot of colleagues from the IDC, but also from PNNL. Yeah, let's start. So what is our problem? Why we are doing such a challenge, and what are possible solutions? So CTPTO IDC is routinely checking air samples for traces of radioxenon, as you all know. But we have to face the fact that xenon is emitted from nuclear underground tests, but also from civil nuclear facilities like power plants. But most importantly, I have to stress that there are the medical isotope production facilities. And if you compare the source term of nuclear underground test and what the isotope production facilities emit per year, you will recognize that there is some issue for us. So these emissions from civil nuclear facilities generate a disturbing background. You only have to think about the minimum detectable concentration, which averages around 1 millibecquerel per cubic meter. And this is particularly true because the discrimination between CTPT relevant events and background based on isotope ratios can be difficult. I mean, there are approaches, but this can still be difficult. But it is often, simply impossible because we are lacking multiple isotope detections. So what is currently done? What are counteractive measures CTPTO is taking? So there are, as you also may have heard, xenon background measurement campaigns. And of course, we can determine the PSR. So these are two things where CTPTO is more independent. But of course, we can also try to model industrial xenon emissions based on pertinent emission data. And this is now the link to the first and second ATM challenge. But what is also done, there is given support by the CTPTO for voluntary xenon emission reduction. This is, of course, another approach. So let's come to the first and second ATM challenge. What was the common purpose? So the common purpose was to ascertain the level of agreement one can achieve between real IMS measurements and those simulated using only the stack release data and ATM. So if we now compare the first challenge in 2015 and the second challenge in 2016, we can state the following differences. So in terms of number of participants, so we had 13 participants in 2015 and 17, but yeah, I just discovered an 18th participant. So now we have in total 18 participants. Emission source and time resolution. So in 2015, we had simply the ERE facility in Belgium, which provided emission data for November 10th until December 8th, with a time resolution of 15 minutes. And for challenge 2016, we changed the hemisphere. Here our source is SnT in Australia, with data from 11th May until 11th June 2016 with a hourly resolution. So now which IMS stations were involved and what is the distance to the source? So in the first ATM challenge, there was only station Schauinsland involved with 380 kilometer distance to the source. And in the previous challenge, we had 6 stations involved with distances ranging between 670 and 13,500 kilometers. Now let's come to the method. So for the challenge 2015, participants simply had to give time series for collection times and the actual emissions were given to them. And in the last challenge, they had to provide time series of dilution factors for individual unit emission releases. So the actual emission releases were not given to them. We tried as much as possible a blind test, and only afterwards these unit emissions were scaled with the actual emissions. Yeah, isotope involved in both challenges is xenon 133. We did some investigations whether we could use also 135, but unfortunately this was not possible. Yeah, and I want to point you to a publication about the challenge 2015 from PNNL, from Paul Esslinger. And for the recent ATM challenge, the publication is in progress. So now a very important topic. So defining a challenge is a challenge in itself. So some people may think, yeah, you now have the emission data and you simply compare those station measurements. But this is not the case. So one needs emission data and simultaneously or slide time shifted IMS samples, and they should preferably not be influenced by not quantified emissions. So what my colleague Yolanda did, she calculated emitter station sensitivities with FlexPath eSIM WF, and they were both processed in WebGrape. And according to this analysis, we could distinguish 3 groups of stations. So there is station AOX04, AOX09, FRX27, and NZX46, which according to this station sensitivity analysis are only influenced by SnT in the time frame which we were interested in. So here we can do a comparison. It's useful to do a comparison. Statistics can be calculated, but of course I have to stress there may be unknown sources. But in the southern hemisphere we are more confident that with the main emitters, yeah, we have captured most of the possible sources. So then there is Rio de Janeiro station BRX11. So here we have no reliable SnT influence, but nevertheless we wanted to add this station. And there was a very interesting case at station GBX68, the island station Tristan da Cunha, which shows a very short SnT influence. And this station was also very interesting because of the big distance to the source. So the distance is 11,900 kilometers. So in this plot, you see an example for the first group, where you have only green stars. This means only influenced by SnT. Here for Rio de Janeiro, yeah, we have only influenced by ESESA. And finally, at GBX68, we have this short slight SnT influence. So now it's time to talk about the participants. They come from all over the world. So as I said, in fact, it's 18 participants from 10 different countries which submitted their results by December 31st. And it was especially nice because 12 of them had already participated in the previous challenge, so we could have a look at the results of the results of these participants for the challenge 2015 and now for the challenge 2016. Yeah, just to give you an overview how the plume developed. So this is 4 days after the first release from SnT. We see how this plume splits into 2 branches. And then, yeah, at May 25th, we see how, yeah, nearly the whole southern hemisphere is covered with this radioxenon cloud. And we find maximum levels of a few millibecquerel. Yeah, of course, it was very important to collect participants' metadata. I do not expect you to read this table, so I will sum up what we have here. So we had up to 6 contributions per organizations. Models used were high split, so for 8 runs, FlexPort for 15 runs. Then the Canadian MLPD was used for 2 runs. Then the French model IDX, the Olarian model IDX was used for 1 run. Then the Met Office model name was used for 1 run. And then there was a high split GEM run, which is a combination between an Olarian and a Lagrangian particle model. NWP data was ISIM-WF, ISIM-WF-ERA interim, NCEP GFS, then yeah, reanalysis data of NCEP, then of course the Canadian meteorological input data GTPS, then we had in one case WRF, of course Arpege, and the Met Office Unified Model Global. Model direction, so 19 runs used a forward setup, 9 used a backward setup. And the horizontal meteorological resolution ranged between 0.125 degrees to 2.5 degrees. And the model output grid ranged between 0.125 degree to 1 degree. Yeah, now let's come to the overall statistics. So what we can see, once again, I'm summing up this table, which then finally will appear in our paper. So we find an overall moderate correlation of 0.53. And this can be attributed to an average time shift of 2 sampling periods. So then we slightly underestimate the measured values, which we see in the fractional bias. The root mean square error does not look very impressive with plus minus 0.4 millibecquerel per cubic meter, but we have to bear in mind that we are predicting very low values, so this absolute value does not mean much. Then I was evaluating the so-called normalized average absolute deviation because especially radionuclide colleagues often ask me, so what is the percentage error? And here I ended up with a value of 191%, which is not uncommon if you compare measured and predicted time series. Yeah, and then we introduced a very simple statistical metric, which is also used by ISIM-WF. We wanted to know how good we can discriminate the detections and non-detections. Yeah, and here we find a very good number of around 80%. Now I split the statistics according to metadata. So I just want to mention the common characteristics with challenge 2015. So the relation of the highest to the average rank was very similar, all for the lower absolute level. Then we found that forward modeling turned out to be better than backward, but maybe there are technical reasons which caused this feature. Yeah, meteorological and output field resolution smaller than 1 degree yields no advantage. And finally, daily resolved emission values do not result in any disadvantage compared to higher resolved values. But I have to emphasize that, of course, this was only a case study. And for our specific setting, these are some common characteristics with the previous challenge. Yeah, then quickly let's have a look at one time series. So this GBX 68 is very interesting station, Tristan da Cunha, because we found some good news that ATM can yield reasonable results even 12,000 kilometers away from the source. I mean, yeah, the values are below MDC, or mainly below MDC. There was just one prediction above MDC. But nevertheless, I think it's a remarkable fact that we get a signal here at this quite remote distance. And this signal is only caused because of an exceptional release from SnT. Otherwise, we would not see anything at this station from SnT. So yeah, then it's time for conclusions. So what are the conclusions? So the performance of individual submissions at individual stations is quite diverse, but this somehow had to be expected. So there exists no single model methodology combination which performs best for all stations. And here I'm assuming daily source time resolution. But the finding of the first challenge that the coarse resolution of methodology, and I want to stress that I'm here talking of the extracted resolutions, because if you use 0.5 eSIM WF data, this is based on a high resolution model. And the coarse resolution of the source daily in this case is not detrimental. This was supported. And as a proof, so the overall best run for challenge 2016 used 1 degree data and daily emission chunks. Yeah, then also the finding that forward simulations here in this special case were superior to backward simulations is supported. Yeah, I had a discussion with a French colleague. She said maybe the collection times influenced this, but this was just an idea. Yeah, then the station statistics do not depend on the distance between the source and the individual stations. I think this is an important message. So the remote stations can have better statistics than close ones. For example, station 27 versus station 04. Yeah, 27 is Babet in the Pacific Ocean, and yeah, EOX04 is an Australian station. Yeah, next conclusion is also important. So if you assume a more conservative uncertainty of around 20% in the daily stack emission values, this does not account for most of the observed deficiencies in the prediction. Yeah, and the average deviation for simulated values, because I'm, as I said, often asked for what is quantity, with measurements or simulations above MDC, it's up to 200%, and yeah, this is of course also influenced by phase shifts of simulations with regard to measurements. Yeah, and as I said, so a paper is in preparation. I hope to submit it during July. So, and finally the outlook. Then I'm finished. So there was an ITM challenge site meeting on June 26th in the frame of SnT. So yeah, we tried to collect participants' views, some feedback about the previous challenge, and ideas how to proceed. Yeah, just to mention this, there are many ideas how to proceed, so I hope we will come to a conclusion soon. Yeah, from a scientific point of view, what I think is very important is that if we have a new scenario, we should have one with multiple IMS stations hit regularly by non-emitters over an extended period. Because the problem we had in the current challenge were the sparse data. But this selection of stations with sparse data was of course closely related to the fact that we only had emission data from one source. If we had emission data from 2 or 3 sources, then it would have been possible to select stations which are more regularly hit by some radionuclide, by a radionuclide plume. So yeah, and this would be very important in order to end up with more significant statistics. And also there is the idea that more model parameters like the methodological driver or the emission segment length, the methodological input and the model output grid resolution should be prescribed for a more coherent analysis, so that yeah, we really are in a position where we can make good comparisons which do not have any deficiencies. So, and with this, I want to thank you for your attention.
We have a few minutes for questions. I guess if you could use the microphones.
So Christian, the 200% average deviation, you said on your slide it says this considering phase shift. Does that mean that's 200% after you have made some correction to obvious?
No, so no correction.
No correction,
no.
So it would be better if...
Yeah, so for the paper I also prepared a column in the statistics table with maximum correlations and then giving the time shift. No, so this is as we would make this comparison in a real case.
Yeah. I think that the statement you made about the role of resolution is not really supported in this generality by the data that we have collected in the challenge, because we would need to keep all other parameters constant and then just vary resolution.
Yeah,
And, like from the way you evaluated the data, that's not the case. Whereas what you can see on our poster, where we just did that, and we see that at least for the closer stations, there is a clear benefit of finer resolution.
Yeah, so I don't contradict. So for the closest station, yeah, but for the remaining stations, it's very questionable. And we were also discussing what we could get from producers, and it's very likely that they will supply us daily values. So we had to make an estimate whether with daily values some reasonable results can be
Yeah, I'm not
found.
only referring to the temporal resolution of the source, I'm also referring in this case to the output grid. Where it's even like more clear. If you look at the poster, yeah, it's really obvious.
Yeah, I mean for specific submissions.
And
it's clear.
as having done the simulation with the highest resolution, horizontal resolution and methodological input, I could say that probably it can be improved still, because we were using, for performance reason, only 3 hourly fields. And if we go to 1 hour, I hope it will become better.
Of course, yeah. I would not
we
contradict.
don't really know, and I think we should be careful not to too easily dismiss the gain from high resolution data.
As I say, you may want to have a sidebar after this to clarify that further. Other questions?
I have a question for the first speaker. Might I ask this now?
Yes,
Okay.
Dr. Bowyer.
So thank you, Ted, for this great talk. I have a question concerning argon 39, which you mentioned in your talk. Could you say something about your thoughts on argon 39? Because I think it has quite a long half-life time, so it must be horrible for measurements.
Right. There is an atmospheric burden of argon 39. Let me try to remember what that is. Roland probably knows it right off the top of his head, and I'm guessing it's in the range of 10 or 20 millibecquerels per cubic meter. But Roland, do you know the answer to that question? 0.1 dpm per liter. Okay, so. Yeah, so there's atmospheric burden. It's got it's a 269-year half-life. So it will, generally speaking, be detected in the atmosphere. I mean, maybe Justin remembers the number, but yeah, it's a point that it'll be in most samples when you're detecting at very low levels, and it will cause an interference to the argon 37 background measurement.
You're not suggesting to measure it as well in the IMS? It's just for background measurements?
Well, I am not necessarily suggesting it. It is not. There's a couple of reasons I'm not suggesting it. One is the atmospheric burden is higher than argon 37. Two, it's not really necessary to measure, except for if you need to subtract its background. The other issue is it's not a relevant radionuclide for on-site inspections, and so that harmony between OSI and IMS doesn't exist. I'm not saying it's a poor idea to measure argon 39. It's just it's got disadvantages compared to argon 37, mainly because of the half-life.
I have a question for you, Ted. Has anyone performed a true calcium variance analysis to really profile the expected range across the spectrum of what we might expect to see?
Yep.
You know, how good or how bad it would be?
It's a good question. That's been done in a number of ways. In the work that Roland and Robin did, they used a worldwide calcium database to do those estimates. So there are worldwide calcium estimates. We've also done calculations in soils from essentially salt, all the which you would think would have almost no calcium, but in fact it has hundreds of parts per million, which still makes it very significant amount of argon-37 produced, actually. So yeah, it's been done in several ways, and unless you can find soil that has zero calcium in it, you're still going to get a significant amount of argon-37.
Okay, thank you.
So Ted,
Stay.
It's an interesting proposition, of course, but I maybe a little bit, if I can be devil's advocate or so. Your argument was built quite extensively on the relationship to the background in comparison with Xenon 133 and so. But what would worry me more from the numbers you showed were just absolute source term, which was a factor of 100 or a factor of 1,000 or so lower. And if I remember correctly, from the MDCs for argon-37 that were flying around earlier, 20 or so millibecquerels per cubic meter, so that's a factor of 100 higher than for xenon.
Yeah.
So it's starting to become like that would be the issue rather than the background, the source, the signal to background.
Yeah, that's an excellent point. I have in my backup slides, one of the issues we're going to need to do is we're going to need to significantly improve the detection limits for IMS by at least a factor of 10, if not 50, in order to solve that problem. And I claim that's scalable, though. You know, we can get as an arbitrarily good detection limit for argon-37, depending on what we do. There's tricks. You can many proportional counters, collect lots of samples. But so our problem is scalable in that way. But that's a good point. I actually have backup slide I could show you. But yeah, they do need to be improved over the OSI systems. This looks like it's for Christian.
Okay, one more question and then we will move to the poster preview.
Yeah, thank you. Ted, I have also a question for you. Yeah, you have argued or suggested to measure argon-37 besides, or compared to xenon 133. And you've showed the advantages or reasoning for that. But of course, also other xenon isotopes are being measured. So could you just comment whether argon-37 is has still an added value compared to all the radioxenon isotopes that are being measured?
The short answer is it's still valuable. If I think it's 2013, is that the one where it was 55 days? I get my year right, but 2013, pretend that wasn't 55 days, pretend that was 85 days. There's basically nothing left besides argon-37, argon-39 if there was calcium, a tiny bit of xenon 131M, just tiny amount, but it's really low, and then some krypton-85, which has a big problem with background. So in that case, argon-37 would be by far the best signature. So everything else has a much shorter half-life. So certainly at longer times, argon has got a huge advantage over the others.
So now we would like to invite all presenters to line up and tell us about the posters.
Yes, if you could line up and be ready to immediately transition to the next poster, because we won't have time for folks to go back and forth. So if you could take a cue.
How many posters do we have?
And the first poster will be P6 from this section.
Good afternoon. My name is Paul Skomorowski from the Austrian Weather Service. In our poster, we will present and discuss the results of a comparison of several atmospheric transport models which were available to the Austrian governmental organization for decision-making purposes during a radiological emergency event. So, yeah. Thank you. More can be seen on the poster. Thank you.
Hi, I'm Eric Piri from CEA, and in this work we investigated the effect of gas-magma interaction in the nuclear cavity on the xenon source term available for migration. So we started with the classical decay chains from indium to xenon and tried to define some solubility coefficient and diffusion coefficient, and we coupled this coefficient with the classical Batman decay chains, and we end up with this result as shown here in the mid right. There is a dramatic effect of gas-magma interaction compared to the without interaction, which is the case on the left over there. And we also performed some numerous simulation for quantitative sensitivity analysis, and we end up with a very strange multi-isotope ratio chart. So if you want more details about this poster, please come, and it will be my pleasure to answer the questions.
Hello, my name is Astrid Suarez from the Air Force Technical Applications Center. They have been a new tool that has been developed by the Air Research Laboratory that incorporates the high-split model inside the computational loop of the WRF model. This allows it to take advantage of the high-frequency meteorological output as well as the native WRF grid. It has been shown to have a lot of advantage for ATD prediction. So here I'm conducting an evaluation of this tool for operational use. I'm doing a verification and validation. I'm also doing an output frequency sensitivity analysis, as well as a parallel scalability analysis for HPC. So if you're interested in these results, please come see me at 1.3P7. Thank you.
Hello, I'm Scott Broom, Sandia National Labs, United States. This work supports the underground nuclear explosion signatures experiment. One project that was performed was a field gas migration study where noble gases were injected at the working point of a legacy nuclear test site. These gases were measured as they traveled through the underground up to the surface. So what this poster presents is we took core samples from that area, and there were 5 lithologies or rock types that we measured gas migration through. And what we found was there's an order of magnitude time difference between the fastest arrival times of the noble gases and the slowest. Thank you.
Hello, Lee Glasgow from Lawrence Livermore National Laboratory, and my poster is Improved Evaluation of Atmospheric Flow and Transport over Complex Terrain at Multiple Scales of Uncertainty. I'm covering 2 topics. One is a high-resolution simulation with LES over a 850-meter high jagged peak in Utah, where we characterize a morning and evening transition. And the second is a more traditional weather atmospheric modeling analysis characterizing the uncertainty using Bayesian methods. Look forward to seeing you in my poster.
Yeah, hello. So topic of this poster has already been mentioned. It is looking a little bit deeper into some details of the recent ATM challenge and specifically to the role of resolution, the resolution in time of the source and the resolution of the output grid that we are using both horizontally and vertically. And I will be very happy to discuss with you whether or not we can see an advantage in higher resolution.
Hello, everyone. So we all know that the Xenon 133 background is mainly stemming from major emitters in medical isotope production and numerous sources from nuclear power plants. And I use data from the first ATM challenge from 2015 to showcase the gain you get when you not only look at stack emission data from major emissions, but also if you also include annual estimates of weak sources into the ATM model to predict concentrations.
Good afternoon. My name is Andy Delclos. I'm from the Royal Meteorological Institute of Belgium,
And together with my colleagues of the Belgian Nuclear Research Center, we did a kind of intercomparison exercise between 3 different dispersion models. This was done within the context of the nuclear and radiological emergency preparedness and response purposes. So we collaborate together on this. As you can see on your right-hand side, you see a dispersion model output of FlexPart. So we did 2 releases on one day. What was very interesting on this day was that there were 2 specific meteorological conditions. So it was very interesting to include them into one day to see how the model will behave on the same day. And as a kind of side exercise, we also, in this CTBT verification regime, we also did an intercomparison by looking at the estimation of the effect of dry deposition only of the iodine, to see how this dry deposition relates to the advantage of the detectability of it, which is roughly 2 orders of magnitude better than the xenon. So because of its lower detectability. So if you are interested in our results, please come and visit poster 15.
Hello again. At the CTBTO, at the International Data Center, we have established the capability to run high-resolution transport modeling in form of FlexPart WRF. And high-resolution ATM uses the conventional meteorological data and folds it with a high-resolution topography and more data of the Earth to create higher resolution data. And on the poster, I show the current status at the IDC of this and some model validations.
Good afternoon. My name is Justin McIntyre. I am not Justin Lowry. I was chosen to talk about his poster because we had the same first name. But that said, this is much in line with what Scott Broom had said earlier for this particular poster. And I'll just say that the one takeaway message that we have for the measurements that we've made so far is that stable tracers such as SF6 behave differently than the noble gases, argon and xenon. And so using them as tracers, as surrogates, there are some differences that we've seen so far in the measurements of diffusion through the subsurface. Thank you.
Thank you very much to all the poster presenters. At this time, that concludes everything that we have for this session. It's about 5 minutes to the next meeting, so thank you very much. I thank my co-chairs for all your help. Oh, one item, this is the first half of this section, and you can go out and see the posters, and then the next half of this session is tomorrow morning. So we'll resume the rest in the morning. Thank you.